We saw Simon's problem last time and a proposed algorithm for it. What was Simon's problem? We had an input, let's say x1 to xn, where n was equal to 2 to the power k, such that each xi was in itself a value between 1 and n. Given this, we were also given a promise that xi is equal to xj if and only if I is equal to j plus s for a hidden shift s. Our task was to find s. This was Simon's problem. We looked at an algorithm for it which looked very much like Dice-Jotsa or Bernstein-Wasrani, but became different in the end. The algorithm was, you start with 0, 0. These are 2k qubits. I apply header mode to convert it into an equal superposition. Then I apply the query oracle to get the answer on each j. This gives me jxj, and then I measure the first register. I measure the second register. This gave me a state which looked like this. I should just say simple plus. This was for some I with equal probability. And then if I applied Fourier transform and measured the first register or the only register left, in that case I get an L uniformly at random. That means each possible L I will get with equal probability. I will get L uniformly and random. But what did this L satisfy? It was perpendicular to the hidden shift L. What we wanted to prove was, if we repeat this iteration, so getting this was called a Simon's iteration. Our objective was that if we repeat Simon's iteration order of log n many times, log n might not suffice, then we get k minus 1 linearly independent L's with high probability. And why was that important? Because once we have these, we have s dot L1 equal to 0, s dot L2 equal to 0, s dot Lk minus 1 equal to 0. And if L1 to Lk minus 1 are linearly independent, this will allow us to give S using Gaussian elimination. This was kind of a short recap of what we did last time. The things we are going to see in this video, one is, why did we get such an error? There is an intuitive meaning of why this kind of an L was obtained. Second thing, to show that we get k minus 1 linearly independent L's with high probability. Remember, log n is equal to k. And the last part is, classically, in the randomized sense, we need lot of queries. That will finish our discussion of Simon's algorithm. The first part, in some sense, is to provide you more intuition and laying the platform for the hidden subgroup problem. I will talk about HSP problem later, but okay, let's see, why did we get such an error? Actually, if you remember last time, the state, I called that as a coset state. All these names will make sense now with a little bit of explanation. In Simon's problem, your xi was equal to xj if I was equal to j plus s. Look at the subgroup or group z2 to the power n. This is the group in which everything is happening. All these indices I plus s are in this group G. And look at the subgroup H, which is generated by 0 and s. This has size 2. The condition which was given to us basically says that my function or x, whichever way you want to put it, you can say xi or fi, we have discussed this multiple times. The function is constant on each coset of H. Let me say it once again. We had G, which was z to the power n, and a hidden subgroup H of a special kind, not all possible subgroups, but of this kind. The condition was that our function f, the oracle was hiding a function. That function had a property. What was the promise? Function was constant on cosets of H. Question, can you find H? Once you put it in this framework, you see that the state I plus s, these two elements are one coset of S, coset of H. And that is why this state is a uniform superposition over cosets. I should say uniform superposition over a particular coset. And that is why this state is called a coset state. Now, from this equal superposition coset state, it is easy to see that if you apply the Fourier transform, what does Fourier transform do? It takes us from the standard basis to the character basis. Then what characters survive? Only those characters survive such that I should say which are trivial on H. This is something which you need to confirm. This is because if you look at chi G, this is non-zero only if chi is trivial. This is happening here. We had a coset state. When we applied Fourier transform, you can see, you can take the group state. The group state would be this. Even here you will see that When you apply Fourier transform, the only characters which will survive will be the one which are trivial on H. Once that happens, then we know that when you measure, you will only get those characters which are trivial on H. This even happens here. The characters in this space are minus 1 to the power L dot A. So chi A of L is this. This is how characters of Z2 to the power n look. And then clearly we said that we will only get characters which are trivial on H. That means L dot S is equal to 0. This is the explanation of why all this is happening. Since we are taking the Fourier transform, this also tells you why did we take the Fourier transform. Given a coset state, Fourier transform will put it into characters which are trivial on the subgroup. Let me write this important property, that Ft on coset state will only give characters which are trivial on H, which are trivial on the subgroup. This is the property which we used, and hence if we think of characters of Z2 to the power n, this will tell us that if the hidden subgroup was 0, s, we get L such that L dot s is equal to 0. Great. This gives us an intuitive definition of what is happening. Let's look at more practical question. How can we say that S dot L1, S dot Lk equal to 0? We can get k minus 1 such linearly independent vectors in order of k Simon's iteration, or from order of k coset states. Remember that each Simon's iteration gives us one coset state. The claim is now when we measure, we take the Fourier transform of coset state and measure, then we will get k minus 1 linearly independent L's or characters with high probability. This is happening with high probability. Let's see why. Suppose at some instance I have these many linearly independent vectors L1 to Li. The space spanned by them will have 2 to the power I vectors. Remember, all this is happening in Z2 to the power n. On the other hand, total number of L's are 2 to the power k minus 1. This is the space or span of L1 to Li. That means probability in the next iteration, probability that we get a linearly independent L is more than 2 to the power k minus 1 divided by 2 to the power, sorry, I should be opposite, 2 to the power I divided by 2 to the power k minus 1, which is greater than half. You can now go in two ways and solve this problem. Let me show in two ways how this probability is high. In the first case, you just say what is the probability that I get n minus 1 linearly independent vectors, one after other. Every vector I get is linearly independent. This happens with probability 1 minus 1 by 2 to the power I. This follows from our previous discussion that if I already have I linearly independent vectors, then I fail with at most this much probability. So I win with at most this much probability. And this is bigger than I equal to 1 to infinity 1 minus 1 by 2 to the power I, and this can be estimated to be 1 by 4 or more than 1 by 4. You can do it even by this formula, or you can do it by more complicated mathematics, but this shows that with 1 by 4 probability you will get n minus 1 linear independent vectors. And now to boost probability, you know this trick, repeat. If you even repeat it constant many times with very high probability, you will get n minus 1 linearly independent vectors. Let us look at another way to show that we have enough probability of getting n minus 1 linearly independent vectors. Let's say every time I do a Simon iteration or I measure a coset state, if I get a linearly independent vector, I call it head. In that case, the probability of head is more than half by what we discussed before. Every time we have whatever be the number of independent vectors obtained till now, if we haven't obtained k minus 1, then with probability at least half, the next vector is going to be linearly independent. So probability of head is more than half. Then the problem becomes, if you toss coin, let's say t times, how many heads will you get? Notice that the expected number of heads would be t by 2. This shows, in other words, if we do the Simon's iteration, let's say 3 times k minus 1 times, the expected number of heads would be 3 by 2 k minus 1, and this will show that we get k minus 1 linearly independent L's with constant probability. I give it as an exercise to prove this. This is an application of Markov's inequality. Once I get that, we just already have the same thing. We say that we get linearly independent k minus 1 vectors with constant probability. How do we boost the probability? We just repeat. This again shows we can get k minus 1 linearly independent vectors with high probability. And how many times did we do the Simon iteration? Order of k. This finishes the quantum part. So quantum query complexity of Simon's algorithm is order of k, which is order of log n. What about randomized query complexity for Simon's problem? It turns out that that is not hard. The question is, you have to do the power k different elements. They can be paired into 2 to the power k minus 1 sets. Now the question is, if we sample from these 2 to the power k elements, when will we see two elements from the same set? You can write down an expression for this. For example, you can say probability that I get to see two elements of the same set after I iterations this happens with probability 1 multiplied by 2 to the k minus 2 divided, sorry, I should say, yeah, to the power k, sorry, let me just say 1, then I have to remove 2, and then I have to take out at most 4 elements, and so on. And this expression should remind you of birthday paradox. I will finish here. You can calculate this probability explicitly, or you can read about birthday paradox. This will show that I should be equal to square root of 2 to the k for this probability to be constant. In other words, if I want my randomized algorithm to succeed, it should make these many queries. This is order. This finishes Simon's algorithm. We realized for Simon's problem, quantumly it can be done in order log n. Classically, even in the randomized model, the best we can do is order of root n. This is an exponential separation in the query framework. We also saw that we could think of Simon's problem as kind of a hidden subgroup in Z to the power. This is going to be very important, and we are going to generalize it next, and we will call this the hidden subgroup problem on finite abelian groups. Thank you.